So I'm filling in for Sanjeev, but it's my real pleasure to have to introduce Professor David Dean, who I met perhaps more than almost 25 years ago in Bombay. He was visiting Satya at TIFR, and we had a lot of fun times together. But and we've of course met since. He's been a frequent visitor to RRI, to Sanjeev's group. So just a few words about his professional life. Professor David Dean carried out his PhD at the Department of Applied Mathematics and Theoretical Physics at the University of Cambridge. After postdocs at the CEA Saclay, La Sapienza Rome, École Normale Paris, and the University Paris Sud, he was recruited at the University of Toulouse in 1998. Since 2012, he's full professor in statistical physics at the Laboratoire d'Ondes et Matières d'Aquitaine, which is at Bordeaux. He works in the areas of statistical physics, stochastic processes, and soft matter physics. He's going to tell us about disruption of screening of thermal van der Waals forces in electrically driven electrolytes.
Okay. Well, thanks very much. It's always a pleasure to be back here and meet up with people I see probably once a year, apart from Satya, who I see rather more often. So I'm going to talk about something. Disruption of screening of van der Waals forces in electrically driven electrolytes. Actually, I gave a talk. The first talk I gave on this was a shorter talk. It was for our physics day at Bordeaux, and it was particularly perturbing because my wife was there, and that's the scariest. And so she said, you have to make a pedagogical effort. And then I'd written unscreening. I'm not sure if unscreening or descreening is a real word. So I decided to put disruption of screening. Okay, so let's start off. So what is screening? I want to talk about screening of van der Waals forces across dielectrics. So actually lots of experiments that were carried out in the 1970s with surface force apparatus. And the sort of system you would look at, you would have two surfaces, which are solid, which would have a dielectric constant epsilon prime. And in between it, you put some liquid, typically this liquid would be water. You look at the separation H, and actually, if you look at the Lifshitz theory for van der Waals forces, there's a component, so there are two components to van der Waals forces. There's a component which is called the thermal component, which is beta is 1 over kBt, so this is proportional to the temperature. So this comes from the classical behavior of the dipoles. There's also a quantum component, and so this is just the purely thermal component. So you can think of it as, having little dipoles which are in this dielectric slab, in this liquid, and the overall interaction is given by this term here. Zeta 3, Satya showed this morning, is the Riemann zeta function. So it turns up in random walks and in the theory of Casimir interactions or van der Waals interactions. So this is the thermal component. So in quantum language, it's the zero Matsubara frequency part of the long range of the van der Waals interaction. And the interesting thing is, of course, you see it goes like 1 over h cubed. So this is interesting because it's a long range force. And so it looks as if there's something critical about this. And so physicists like this sort of interaction, okay? So this is what happens when you put water or any sort of liquid. You could put ethanol or anything, okay? So you have this long-range interaction. Now, the interesting thing is, of course, in most situations, water always comes along with a bit of salt, even though it's difficult to get rid of it. So here are my cations and my anions. So you put in this salt solution, so this could be sodium chloride, okay? And actually what you find is that this thermal component of the van der Waals interaction, so there's still a long-range component, which is the one I just showed you over here. And as I said, this is typically 50% of the interaction for water. So the quantum parts typically give you another 50%, okay? But actually, this thermal component, which comes from the classical nature of the dipoles in your system, if you work out what this force per unit area, or this is essentially the disjoining pressure, so people are doing soft matter, is given by this formula here. So this looks a bit complicated. But if you look at what happens at large distances, you see that rather than having a 1 over h cubed decay, it now decays like exponential of minus 2 mh. And this M, this is called the inverse Debye screening length, okay? So this depends on the average density, number density of your electrolyte. So this is a symmetric electrolyte. I've got 2 rho bar. So rho bar is the average density of the anions and the cations. Q squared is just the charge, and this is just divided by epsilon, which is the dielectric constant of your water, for instance, and kBT, okay? So it's an amazing effect. So you have this long-range interaction, you put a little bit of salt in there, and it disappears completely, okay? And so this computation can be carried out using the Lifshitz theory, which to a certain extent hides some of the physics. So I'm going to discuss another way of deriving this.
At high temperature, the guy goes to zero, right? M goes to zero.
M goes, yeah, M would go to 0 at high temperature, yeah.
But in high temperature, you still have the normal van der Waals,
Yeah, yeah, yeah. Oh, no. Well, this M, even though this M is small, right? It's still, okay? So this is a bad cartoon of screening, right? So you have to think that van der Waals interactions are due to dipoles. So if you think about dipoles, they're just 2 charges, right? On a spring, if you think of a simple case. So the cartoon of screening, what happens is that if I put 2 charges, Q1 and Q2 in my system, and imagine that they're both positive charges. See, the anions, they come and screen the charge, and they'll screen it on this side. And actually, it's well known that the effective interaction between these 2 intruder charges, rather than being the Coulomb interaction, is actually this screened interaction. Okay? So somehow, the calculation, the screening that I showed you on the last transparency, is happening because basically, at the sort of at the classical level, you just have dipoles in these dielectrics. They're fluctuating, and dipoles are just positive charges hanging on to negative charges with the spring, and so this is why you would expect some sort of screening. Okay. Now, how do you understand, if you wanted to do the Lifshitz calculation, how do you understand this? Well, actually, what you can show is if you write down the field theory, the zero frequency part of QED, basically what you have is this is the electrostatic field term here, and now what you have a coupling to the charge distribution in the system. And the charge distribution, so there's an I here which gives you the repulsive nature of the Coulomb interaction when you do the integral over the field phi. It introduces the interaction between the charges. This is the charge density coming from the dipole, so there's a div P here. And a way of modeling a dielectric system is just to say that in each area of my region, each region of my system, my dipoles are basically, they just have a quadratic Hamiltonian, okay? So this 1 over chi of x, it depends on where I am. This is just the local polarizability, okay? So now what you can do is, now what actually happens, right, when I'm talking about the thermal part of the van der Waals interaction, now what you're assuming when you do the calculation is that the dipole degrees of freedom, they equilibrate with respect to the charge fluctuations due to the fluid. So you have ions which are moving very, very slowly because they're diffusing. You have very small microscopic degrees of freedom, which are dipoles, which are flipping. So that basically, as an assumption in this theory, is that the dipoles are instantaneously in thermal equilibrium with the charge distribution of your electrolyte as if the electrolyte is fixed, okay? So what you can do is you can work out then an effective theory for what's happening with your charge distribution. So actually, if you do this integral, what happens, if you do the dipole degrees of freedom, all it does is it gives you a local dielectric constant here. If you see, if I do this integral here, this is p dot grad phi, I do this Gaussian integral part, it just puts a chi grad phi squared here, which is the renormalization of the dielectric constant. So instead of having the dielectric constant of the vacuum, you have the dielectric constant of your medium, and then you still have the coupling to the local charge distribution, the mobile charge distribution, which is your ions, okay? So this is the effective theory. So,
Sorry, so you have a dielectric constant which is now a function of position.
yeah, so for instance, chi would be one thing in the top slab, it'd be something else in the bottom slab, something else in the middle slab. So this would just give you the local dielectric constant of the slab. So this is a cheap way of making a dielectric theory, okay? And so the interesting thing is so when you look at this, So there are now two contributions because when I do the integral over the field phi, I basically, you're doing a Gaussian integral here, right? You're doing a Gaussian integral over this field phi, which gives you a determinant, and you're basically, if this is like x, this is like y dot x, right? This is the Gaussian measure. So basically, when you do this, if you called this A, if this was a matrix A and this was a coupling yx, you just get the determinant of a to the minus a half, x a to the minus 1x, okay? So it's just a Gaussian integral. So if you do that in a functional setting, you get the determinant z vdw van der Waals, okay? And then the interaction that you get when you do the integral between the charge over the field phi, it introduces this interaction between the charge distribution, and in the absence of any dielectric discontinuities, this would just be the Green's function in the vacuum. But because you've got this dielectric discontinuity, this is actually the Green's function which corresponds to the slab problem. So when you write down the Green's function which corresponds with dielectric discontinuities, what you're basically taking into account is image charges, okay? So this Green's function contains all the information about the image charges. So basically what I'm doing is I'm saying if I have a certain charge distribution, I get if just doing the integral over the fluctuations gives me a van der Waals contribution, which I'd have even in the absence of a charge distribution. So I would get this even if the charge was not there. That would be the charge distribution. That's the van der Waals forces that I showed you on the first, okay? But the idea of adding the electrolyte is basically adding in this term here, okay? So this is the van der Waals contribution, and this would give you the van der Waals free energy. If I take the derivative of this van der Waals free energy with respect to the plate separation, this would give me this van der Waals force that I showed you.
So this charge distribution is independent of the potential distribution?
Of the potential distribution, of the dipole distribution. It is, yeah, basically yes, it's independent, other than the fact that you take into account the dielectric discontinuities, okay? So the dipole distribution is modifying the effective interaction between the charges. This is why you get image charges, okay? Okay, so this is what you have. And so you can work out this thermal van der Waals form. So you take the derivative with respect to h, it gives you this pressure. So this is the free energy per unit area, and it gives you a bulk H independent term, which normally you don't look at because in experiments there's a disjoining pressure, and as you squeeze the system, the bulk pressure doesn't count because liquid flows in and out. Okay, and there are lots of different ways to compute this. Okay, now let's have a look at the ion. Now nobody would do the calculation this way. Normally I would do the integral over the ionic distribution and then do the integral over the field phi. That's Lifshitz theory. But what I want to do is I want to have a theory which, I want to build a non-equilibrium theory which takes into account the fact that I can drive the charges in the system out of equilibrium by applying an electric field and have a current, okay? So let's do this. If I look at the ionic contribution, actually what you can show is, you can show that the effective theory, so I'm going to do something which is the equivalent of Debye-Huckel theory. I have to integrate over the charge distributions rho plus and rho minus. I have these entropy terms here, and this is the direct interaction. This is this Q times rho plus minus rho minus. This is the charge density, okay? So this is just an entropic term coming from the plus and the minus, and this is just the direct interaction between the charge density, as you would guess, okay? But you have to remember there is this van der Waals interaction, which is just sitting there on top additively. Now, if you do Debye-Huckel theory, one way to do it is you just expand the density in terms of a uniform background plus small charge fluctuations. So this gives you an effective quadratic theory here, which I've written in terms of the total density and the density difference. So it just looks like this. So you see you have a completely quadratic theory, and now you can just do the integral over the fluctuations to compute the ionic contribution. So on my partition function, I have a van der Waals contribution and an ionic contribution. Now remember, the van der Waals contribution, which I've told you is there, I've just showed you that it's a long-range attractive interaction. Okay? But I know I know this should be screened. I know I shouldn't have a long-range interaction. So actually, when I do this functional integral, what you actually find is that the force or the pressure due to the ions is given by exactly this screen term plus a repulsive universal van der Waals interaction, which cancels off exactly with the fluctuations, the attraction that comes from the fluctuations of the dipoles. Okay, so actually this was pointed out by Jankovici and Shamaj. So this is so viewed from this point of view, you can see that if you do the Lifshitz theory, it's a great toolbox, but you miss some of the physics. So the important thing here is that you see screening because the ionic charges manage to cancel out exactly the long-range attractive van der Waals forces. So they produce a repulsion, okay? And this repulsion, and this is all you're left with, okay? So I think this is, from this point of view, screening of thermal van der Waals forces is quite miraculous, right? There's a real balance going on here, okay, that you don't see if you don't do this decomposition into ions and into dipole fluctuations, okay? So this is an important thing. Now, so the thing is, because this is such a delicate balance, what happens if you decide to push the system out of equilibrium? And if you have ions, what you can do is you can take, well, so this was a model which was introduced by these authors here. So you can basically take an electric field, so I have exactly the same setup I showed you before, and I'm just going to apply an electric field. I'm going to apply an electric field parallel to the plates. So I can imagine plugging an electrode here, and having a current running through here. So the question is, what happens to the interaction between those two slabs when you apply an electric field and push the ionic component out of equilibrium? So let's see. So this, this is, the Lifshitz theory is nice because everything is self-contained, but if you want to do outer equilibrium dynamics, the first thing you need to do is to write down a dynamical model. So I'm going to show we're going to use a Brownian model for the ions. You could potentially put in hydrodynamic interactions, do something a bit more sophisticated. You need to generalize Debye-Huckel theory to out of equilibrium. So Debye-Huckel theory was the theory which is the input to the Lifshitz theory, which shows you screening, okay? Now, if the concentration is not big enough, then you go to a regime where you have strong coupling, and Debye-Huckel theory would no longer work. But you know that Debye-Huckel theory works pretty well, right? If you do soft condensed matter, Debye-Huckel theory, any sort of experiment, you try and you fit it with Debye-Huckel theory, and of course you put yourself in a regime of having the right salt concentration that it works, okay? So we need to generalize Debye-Huckel theory to out of equilibrium, and actually what's been known for some time is there's something called stochastic density functional theory, which I'll explain, and if you linearize it to make the theory soluble, then you get a dynamical form of Debye-Huckel theory. So you have a theory which you know works very well in equilibrium, which then has an extension out of equilibrium. The third thing you have to do is you need to compute forces out of equilibrium, okay? Because you don't have free energies to compute forces, so what you have to do is you have to use a non-equilibrium formulation for the stress tensor derived from body forces. So in principle, you can use the Maxwell stress tensor, but there's an extra component. Because you have an electrolyte, it's not just the Maxwell stress tensor. This is an important point that was missed. Okay, so this is the work that was done here. It's just appeared in PRL with my colleagues people I work with in Beijing. Okay, so let's have a look. Brownian dynamics. So this is my model. So I have ions in a solvent, water in this case. So each ion has a Basel-Langevin equation. So dxi, this is the label of the ion. This is its spatial component. This is its diffusion constant. So beta times its diffusion constant is the mobility. F is the force acting on the ion. And this is the usual white noise term, okay? So if I didn't have any forces, these would just be free Brownian particles. So these forces, they include the external forces. So if I apply an electric field, that will be an external force. If I was doing colloids, I have gravity. And here I have an interaction between particles of type mu and v. Okay, so if I only have one type of particle, there's only one v here. Obviously, if I have charges plus and minus, then there's a q nu here. Okay, so this is the model that I'm going to use. No, actually, so all the dipole forces are in the Green's function. Okay, so when you in this model, okay, so actually, yeah, in this model there are no dipole forces, and actually, so I've written something which is a bit misleading here. I've written, yeah, in fact, I should have put x mu comma x nu, okay, because it's not translationally invariant. What I want here is the Green's function. So this would apply if I use the Green's function for the interaction between the ions. But you're right that when you have a dielectric discontinuity, the potential isn't translationally invariant like that, okay, because you have the image charges, but this applies if you have the Green's function as well. Okay. So let's have a look. The dynamics of the density field. So this is what I call stochastic density functional theory. So what you do is you define the density of the field of species alpha. So in the case we are thinking, you have two types of species. Alpha is plus and minus for cations and anions. So this is just the sum of the delta functions for all the ions of that type. Okay, so this is the definition of the density in a purely mathematical term. If I define a free energy functional, so this looks like the ideal gas free entropy. It would be if I replace this by the average value, but this is an operator here. And then you have the interaction between all your particles. You see I put a comma here now so for the Green's function. And in the presence of an external force, what you can show is that the density field obeys the following equation. For each species, d rho alpha by dt. So you can see it has this d alpha is the diffusion constant of the ions. You see you have this mobility coefficient here actually depends on the density rho alpha. Okay, and then this term here is the gradient of the functional derivative of H with respect to rho alpha, which is effectively the local chemical potential of the species alpha. Okay. This is the term which comes from the external force, which is easy, and this is the noise. So the noise in this system is particularly vicious because it actually has a multiplicative form and it actually depends on the density rho alpha. Okay, so you can see that this differential, you can actually show that the operator acting on grad dH, the operator acting on dH by d rho alpha is actually the correlation function of this noise term, as you would guess from on the Onsager relation. And so this noise now is not just white noise, it's temporal white noise, it's spatiotemporal white noise, which has this correlation function here. So formally you can show that this is exactly the equation that density obeys. And this has been used in lots of different situations. It was used by the chemical physics community to develop what they call dynamical density functional theory, which is an averaged form. You can use it to derive mode coupling theory. You can apply it to active particle systems. You can use to calculate tracer diffusion constants. You use it in random matrix theory, and Satya did this. Okay, so it has many applications. Okay, so the linearized form actually is equivalent. It gives you a dynamical version of Debye-Huckel theory. So what you do is if you expand in terms of the fluctuations about the mean density, if you look to leading order, what you have is the noise term, which is horrible. You can just replace this by the average value of rho. And then this term here, which depending on rho is just replaced by the average value. And then you have the functional derivative of the fluctuate, so the quadratic Hamiltonian expanded to quadratic order in the fluctuations. Okay? So this is the linearization of here, and then of course the term with the force, that doesn't change, okay? So this is what you get. So HF is the Hamiltonian expanded to quadratic order in density fluctuations. And here F alpha is equal to Q alpha times E. So this is the force which would be induced on an ion just by the external applied electric field. Depends on the local electric field and the charge. Now the other thing which is a bit complicated in this system is that you need to impose no flux boundary conditions at the surfaces. Of course, when you write down, so normally these theories you do in bulk, but if you have an upper surface, you have to make sure there's no current. Okay? Now, you don't have to do that in equilibrium, because equilibrium means there are no currents, right? So when you do equilibrium statistical mechanics, you don't tell your students, okay, write out the partition function, we have to make sure there's no flux going through the surface, because equilibrium tells you there's no, so you don't have to worry about that. But out of equilibrium, you do have to worry about that. So you have to do that. So this is one of the difficulties. Now let me go back. So this was work I did with Vincent Demery on the conductivity of strong electrolytes from stochastic density functional theory. So we basically revisited the Onsager theory of electrolyte conductivity. And if you look at the Brownian case, you can actually... No, there shouldn't be. There'll be current in this direction, but there should be no current. The particles can't leave, right? Well, sorry, I don't understand. No, no, yeah. So you have to impose it, right? You have to when you write down your theory for your, you have to tell the system. You have to tell the system that, of course, everything moves that way, but a particle can't move out, right? So normally in statistical mechanics, you don't think about that. It's not something you have to apply. But when you're writing down a diffusion equation, because you have a boundary, you have to impose the boundary condition. Okay. So you have to say that j dot n is equal to 0. Okay, at the surface. But if you do equilibrium statistical mechanics, you never have to do that because j is 0 everywhere. Okay? So this is one of the subtle points. And it actually makes the problem very complicated in general. Seems innocent, but... So what I've got here is this is the pair correlation function. So this is for different values of the electric field. So this is dimensional, the dimensions taken off. Okay? And so basically, so this is H++. So this is related to the probability. If I have a positive ion here, that I will find a positive ion close to it. Now you see it's normalized by the mean density. So this is negative, right? So basically it means that because it's blue, if I have an ion here, I'm very, very unlikely to have another ion of the same charge next to it. So this is like a depletion zone where I don't want to have another cation. Now if you apply an electric field in this direction, so the electric field's going this way, this is the direction perpendicular to the electric field, you can see that you start deforming this probability distribution. If I shifted its probability density function, you can see I get something rather non-trivial, okay? I start, increasing, so you can see that the probability is low here, and what I'm doing is I'm increasing the probability to have ions of the same sign here. So this is a tendency towards forming like chains of soldiers that are walking after each other, okay? Okay, and you can see a similar effect with a positive, and this is H plus minus, so this is the probability that I have a negative ion if I have a positive ion. You can see that obviously I'm increasing the density. If I put a positive ion here, I have lots of negative ions, or negative ions that want to come here, and this is the effect of applying the field. You can see that you're really deforming this correlation function a lot. So what I was telling you about screening is basically this, when I was talking about charges in this. So this is basically, rather than the cartoon, the bad cartoon of screening, this is it, right? You're more likely to have a negative charge next to a positive charge, less likely to have a positive charge. So this is the mechanism. So when you see this, you think, well, if I apply an electric field, if I'm changing, certainly the theory of screening is being changed just by looking at these pictures. Okay, so let's investigate what happens. So going on to sing the praises of stochastic density functional theory as well, if you extend what I did with Vincent and you actually decide to go and fit the data, you can see you have extremely good fits of the data using a modified version of this theory, because actually, in contrast to the Onsager theory, it's very easy to incorporate other interactions. So you can put steric effects into the problem, and so they managed to fit this conductivity data up to very high salt concentrations. So the dashed line is the early Onsager theory. You can see how you can improve the theory, basically fit the experiments much better. And you can also apply it to calculate the viscosity of electrolytes as well. There's a similar calculation to calculate the viscosity. So this is the extension using SDFT. This is the early work by Falkenhagen. You can see you can really get extremely good data on the viscosities of electrolyte solutions. So so theory works quite well. So let's have a look in this theory here. So this is my linearized stochastic density functional theory. So when I look at these charge fluctuations, so when I write n plus, this can be positive or negative, okay? Once I take off the average charge distribution, the charge fluctuations due to positive ions can be negative and positive, and the charge fluctuations due to negative ions can be positive and negative. Okay, so this is what your theory looks like. So you have this. So if you look at these terms here, so this is just the usual diffusion term that you would have if, nothing, if there were no interactions. This is the term, this is the electrostatic interaction, which actually only enters in the linearized theory via the electric field, but the electrostatic potential. The electrostatic potential here obeys Poisson's equation, okay, with the epsilon x here. So it means when I solve this equation, the Green's function for this, the solution to this equation for a delta function source is taking into account image charges, okay? So you have the interaction with the image charges, okay? This is the external electric field acting on the positive ions. This is the external electric field acting on the negative ions. And this is the noise term. So you can actually see, this is a linear function of n. So I basically have a theory which is linear in density fluctuations with a Gaussian noise, so it means my theory is Gaussian. Okay, but your theory is still quite complicated, right? You still have to solve this theory. You have the no-flux boundary conditions at the surfaces. So I've written this in terms of ND is the difference in the charge densities, n plus minus n minus. And sorry, this should be n total. So this is the boundary, so this is essentially the charge fluctuation term. You see the boundary condition here is that the normal derivative, so it's this flux term here, it's basically the difference of these two equations. This term here plus this term here should be equal to 0. This should be a t, this is the, this is the total, yeah, this is the difference, and this is the total charge. This is n plus plus n minus, sorry, there's a mistake here. Okay, so when you look at these boundary conditions, what you find is that this must be equal to 0. So this is fine. This is a Neumann boundary condition for the total density. And also the noise has to be 0 because you see the current has two terms as a sort of deterministic term. Sorry. Has a deterministic term, which is the first term, and this is the noise term. So now the noise term, you have to impose the essentially Neumann boundary condition. So actually what makes this problem soluble is that when epsilon prime is much, much less than epsilon, you can basically say that this term is equal to 0. So you can say that d phi by dz is 0. So this means that if you have a system with a very low dielectric constant, there's no electric field that goes into it, right? Okay, so the perpendicular component of the electric field is 0. And so this is in the dielectric slab, this is in the electrolyte. So it means that d phi by dz is equal to 0. So it means that all of these fields can be expanded in terms of Koch. Okay? And so now the next thing is, how do you compute the forces out of equilibrium? Now this is a subtle point, because you can't just use the Maxwell stress tensor, because there are other stresses. There's osmotic stress, okay? So actually, in this paper, actually, what we showed is if you have a general theory, there's a way of computing the body force, okay? And actually, so it's actually quite a nice idea. So if you imagine have any field theory, and I don't necessarily know what the forces are, right? So if I give you some field, all I tell you is what the density is. So I need to know what corresponds to the density. So I have some sort of theory like this, and I have one case. It depends on h rho, right? So I want to know what the body force acting on a volume of my fluid is. Okay? So the way to do that is what you do is you say, well, actually, let me cancel off all of the body forces by applying an external potential, which I'll call psi. Okay? So let me just modify this Hamiltonian here. And so if I want this system to be in equilibrium, then psi, if I take the functional derivative of this must be equal to 0, okay? That will put my system in equilibrium, okay? And this tells me that the potential psi that I need to apply is equal to dH by d rho, okay? And so the body force that's been generated by this potential here is just rho times the gradient of psi, okay? And so this means that the body force, so the body force is just equal to is just equal to rho times the gradient of dH by d rho. Okay, so you just apply that argument. If you have several fields, you can apply it several times. So what you actually find is the first thing you write down is the body force, okay? And I added on an extra term coming from the external field, okay? So this is basically just the local force. And actually, once you have this expression, okay, which is valid for any configuration, so it's valid out of equilibrium, you can then go and try and write the body force in terms of the divergence of a stress tensor, okay? After that, it's just algebra. So you keep this term here. So this is the term which is coming from the interactions due to all the ions. This is the term coming from the external electric field. And actually what you find is, so you rederive this, you can rederive the Maxwell stress tensor. There's no surprise that this term should be here. You know it has to be here. What is surprising is that you get this term here. Okay, so this is a term coming from density fluctuations. And if you don't put this term in, you don't get the right answer. Okay, you don't get the equilibrium theory. Okay, so one of the things that's important, I'm developing an out of equilibrium theory, which is sort of having to do lots of things, but this should give me the equilibrium screen result, okay? So now if I want to calculate the iron, I can just look at the stress tensor, you know, just look at the discontinuity in the stress tensor, say at the lower surface, so I just compute this object here, and this is giving me the contribution which comes from the ions is KBT divided by 4 rho bar. I've written it in terms of the total and the difference in the density, so you have these terms here, okay?
Excuse me, there is a Walters equation.
Sorry?
Walters equation. Walters. Emil Walters.
Yeah?
Emil Walters equation, the technical calculator shows the synergic tensor.
Yeah, sorry.
Hello.
Yes.
No, there's a question.
Oh yeah. It's but okay. So yeah, but actually, so there's actually a slight subtlety about using Noether's equation out of equilibrium. You can't actually just use it like that actually, because you throw away the term which is due to the Maxwell equations. You say that's equal to 0, okay?
Yeah.
And actually, but out of equilibrium, I don't have any equation which has to be 0 here, okay? So it's subtle. So you can't really apply it. You can apply it in the context you're looking at. You know, I know how you derive it, but here, when you derive the stress tensor, you throw away a term which corresponds to the Maxwell equation, being 0, right? There's the equation of motion which is 0,
Yes.
and so here you can't do that because your system is driven by noise, right? There's no deterministic equation of motion you can throw away.
Okay.
Okay, so that's the subtlety. Okay, and in fact, I think in fact we can discuss this. I can actually show you for a general theory. There's a term in an out of equilibrium stress tensor you have to keep, which would, if you were doing electrodynamics, you would throw away.
Then there is a more change of symmetry also in your problem.
Well, no, I'm not applying any. I'm just doing forces. Okay, and actually, I think that this in this context is the better way of doing it. Okay. Okay. So this is the expression that you have for the ions. Okay. And so you see you have this osmotic term and you have this term which comes from the parallel gradient of the electrostatic field. And so because there's only density above the plate and epsilon is 0 below the plate, so you don't see any of the other terms. Okay. Now, I said to my wife when I gave this talk, she said, you just showed lots of equations. I said, but I didn't show any calculations. I'm not showing any of the details of the calculations. Okay? So all I'm telling you about is the equations that you need to solve. Okay? So actually, what you actually find is that for symmetric electrolytes, you find that the total force is equal to KBT, so it's a thermal force still, divided by H. Then you have 3 directions. You Fourier transform parallel to the surfaces, and you have modes which are perpendicular to the surfaces. Sorry?
What do you mean by symmetric electrolytes?
Oh, sorry, yes, so symmetric electrolytes. So they're not very realistic. Symmetric electrolytes are electrolytes where the positive and the negative, the cations and the anions, are actually physically identical apart from the fact that they have opposing charges. Okay? Now actually, it's just that the algebra is slightly simpler in this case. You can actually generalize this calculation to look at a system of electrolytes where, so actually typically you can generalize this to have different valencies of salt, and you can also have different diffusion constants, okay? I'll show you the result, but I'm just showing the calculation for the for the single species, okay? So it all goes, so in principle, yeah, everybody knows that, you know, some ions are more hydrated than others, right? So, you know, Na plus and Cl minus is bigger, right, I think, than Na plus, okay? Because it has a hydration there, okay? So this is a sort of simple, but it doesn't matter, actually, okay? So let's have a look. So, and remember I said that I could expand all of my, I could expand my currents in terms of these modes n pi over h, okay? And so this is what you get. So you have this expression here. So this is a continuum integral, and this is a sum, okay? And it's crucial that the mode coming from the Neumann boundary condition on density and electric potential, right? If I can't do this, this allows me to do an expansion in terms of a single set of eigenfunctions. Otherwise, I have to look at a fourth order differential operator, right? So basically here, what I've got is two second order differential operators which commute, so I can use the same basis of eigenfunctions. Okay, so when you look at this, you work out what these terms look like. So this k squared, so big K squared here is just, this is just little k squared plus m squared, where m is this inverse Debye screening length, okay? So this is where the screening normally comes from in this term here, okay? So this is just, so big K squared just means this, okay? So normally this is, in fact, when you do the calculation in the simple case, you know, this is the presence of this m squared is what's leading to screening, okay? So actually, if I look at this, so you can see there are lots of horrible terms, and actually this sum you can actually do, okay? There's actually a functional expression for it, but it actually takes longer to write out than it does to write out the sum, okay? And it looks absolutely horrible. Now, the first thing is I've done all this. If I set e equal to 0 and do this integral, I find exactly the screened Casimir interaction. Now, when I say that, I don't find exactly. What I find is I find a repulsive van der Waals interaction plus a screened Casimir interaction. The repulsive van der Waals interaction cancels with the contribution coming from the dipoles. Because these two theories, right, the dipoles and the ions at this level of the theory, they're just doing their own thing now. The dipoles are just influencing the ions via the screening, via the Green's function, right? The fact that I'm solving a Poisson equation which has image charges. Okay, so my theory gives me the classical Lifshitz theory for the screened van der Waals interaction between two dielectric slabs when I've got electrolytes. So that's already a good thing, right? That you can get this. In fact, it must, if you've done the calculation properly, it must do that. There's no way you can, okay? Now, the amazing thing about this is that, so when it simplifies for e equals 0, but there's also what I call a fabulous simplification for the case of large h. So normally you'd be interested in what happens when the length is much bigger than the Debye screening length, okay? And actually, when you look at this, this is the formula that you get. So you had something that looked really, really horrible. You do all this algebra, and you find an amazingly simple result. So this is the total. This is ft. So I've added on the ionic contribution, and I've subtracted off the van der Waals interaction. Okay. So this is the formula that you get. This is the way we wrote it. There are lots of different. So let's have a look. So this is where the electric field is. Okay. Yeah.
D never appears in this expression.
No, it doesn't. D disappears.
Is it possible that they can also write down equivalent theory instead of writing Coulomb motion or equivalent theory?
Well, I will discuss that, right? Well, actually, no. So this part here, this is the long range part, right? So this is the long range part, and you can see, as Anupam pointed out, this only depends on equilibrium value constants, right? It depends on the Debye screening length, the charge, E, right? In fact, you can even write it here. If you write it this way, you can see that this is like epsilon E squared over 2 is like a Maxwell stress, a Maxwell pressure, and rho kBT is like an ideal gas pressure, right? And as you say, there's no D in here, right? The D can appear in the screen component, okay? In principle, but actually, but the thing is, I was doing symmetric electrolytes, right? If you look at the Onsager theory, if you look at symmetric electrolytes, you don't see any effect of the D's beyond the naive one, right? But actually, I'll show you this formula still holds for non-symmetric electrolytes, okay? So, but this long-range component doesn't depend on the dynamics of the ions, even though the system is in equilibrium.
Excuse me.
Yeah?
Sorry.
Yeah.
I not be understanding correctly. You can actually, at the end of the day, will you measure the conductivity of the electrolyte or not?
Sorry?
Preserve the conductivity of the electrolyte or not?
At the end of the day.
The conductivity. The conductivity of an electrolyte changes when you apply an electric field.
Yes.
Yeah.
In study here,
Yeah, yeah. Yeah,
in study any figure here.
the conductivity of an electrolyte increases as you increase the electric field.
But the in detail variation of it with electric field.
Well, well, I'm not computing the conductivity here.
Okay.
Okay.
Sorry for.
Okay, I've written another paper where I computed the conductivity. In fact, you can compute the conductivity, okay? And the conductivity actually increases as you increase the electric field, okay? You can show that sigma of, you know, if you write the current is equal to sigma of E times E, sigma of E actually increases as E increases. Okay, this is known since Onsaga. Okay, this is the E field dependence of the conductivity. Okay, so you can see that there's lots of different ways of writing this. So you find this is beta E squared Q squared over M squared, or you can write it this way here. So you can see straight away that if if you set E equal to 0, the long range part goes to 0. So it completely disappears when you put. And if you take and if you look at the expansion, you can see that for small e, this long range component is repulsive and it switches on like this. So it goes like the magnitude of the screen van der Waals interaction, okay, but it's now of the unscreened van der Waals interaction times this term here. So it switches on, it goes like E squared for small e. Saturates for large E, and at large E, actually, you can actually do the, so at large E, you can do the calculation including the screen component, right? So actually what happens is that you find that the force at very large E is the repulsive van der Waals, long-range van der Waals contribution, which remember comes from the fact that each ionic species produced a repulsive, no, sorry, it comes from the calculation, right? You find that this term here, when you set E, sorry, I'm saying this the wrong way. When you set E goes to infinity, you just have this term here, but you also can compute the screen term. Now, when you look at the screen term, you have a factor of 2, and the Debye mass is divided by the square root of 2.
Can I ask you a question? So this first line, you know, this formula is valid for large H, right? That's what you're looking at.
Yeah.
And E fixed. Okay.
Yeah.
And then when you take the E goes to 0 limit, you see that it has a scaling, which is 1 over H cubed times E squared.
Yeah.
So this suggests there is a scaling function.
Yes. So you always want to be in a limit of large.
Right.
Large.
But in general, for, I mean, H large and E small or something, probably you can write it as a scaling form, like 1 over H cube into some function of E over H to the power 3 by 2 or something like that.
Yeah.
I see.
I'm sure. Yeah, I'm sure you.
Yeah.
If you have to.
Because that sort of tells you a characteristic, distance, because H scales like E to the power 2/3 here, right?
Yeah.
You see from your formula there. So I don't know, this one, you see the 1 over H cube times E square, right?
Yeah.
So it suggests that there is this sort of, H star, which scales like E to the power 2/3, right?
Yeah. That's.
So
Yeah.
if you write down the scaling form, so there's a characteristic, these things which depends on the electric field E.
Yeah.
And, it somehow sort of length increases
Right.
as you...
But but in this formula here, right, they're just two factors which are multiplying each other. Yeah.
But I'm saying that if you don't take, because here you got this behavior by taking large H limit but keeping E fixed.
Yeah, that's
But I'm
true.
saying that if you do it in a scaling way, combination, some
That's true,
keeping
yeah.
ratio fixed, you will get a non-trivial scaling function connecting the two limits, basically.
Yeah. But actually, I'll show you. So you get this result here, and then you get the screen. So if you look at this term here, so normally if I had one electrolyte I would have a factor, normally, you know, the formula, it's unscreened, right? So this term's, there's a screening, so this term isn't here. And normally you have a factor of 1 here, okay? So actually what this is actually coming from, this is actually 2 times the screened Casimir effect for a density of rho bar over 2. So it's almost as if you have a long-range repulsion, and it's almost as if you have 2 independent attractive Coulomb interactions, okay? So this is because the anions and the cations decouple. So there's an incredibly simple explanation for this large result here, okay? So if I forget this term here, so let's go and see it. So it's a decoupling mechanism. So imagine now what happens if I apply a large electric field, okay? So in a large electric field, right, all of the cations are going to go this way, all of the anions are going to go this way, okay? And so they're going to move, the cations are going to move with first order, a speed which is q beta d times E. Okay, this is just the mobility times the charge times the electric field. So if you're looking, if you did a numerical simulation, right, you would see all the anions would be moving like this, all the cations would be moving like this, okay? And basically what this means is when it's very large, you see the only way in which the anions can, the only guys that the anions can equilibrate with are the anions with it, because they can still feel each other because they're locally moving with the same velocity. This is, I mean, if I only had one species of ion, I would have no effect, right? I would just go into the rest frame of the ions and everything would be in equilibrium. So basically what's happening is, I can go into the rest frame of these ions here, and they can talk to each other because they're moving at the same velocity, they're on the same train. These guys here, they're on a different train, so they don't talk to each other. They don't see each other. So when you apply a large electric field, what you're actually doing is saying, well, actually, I'm going to write down a theory of charge density fluctuations where the positive ions interact, the positive charge density fluctuations interact with the positive charge density fluctuations because they're moving in the same frame. The negative charge density fluctuations are interacting with each other. But you see, before I had a cross term. Normally when you do electrostatics, right, the pluses interact with the pluses and they interact with the minuses. But I say, look at this theory here, and I say just say because of this decoupling, they don't see each other anymore. And you get exactly the same result. So this explains physically why you're getting this. So basically, why do you find a repulsive van der Waals interaction? It means that if you have a single set of charge fluctuation, which is only 1, it gives you 1 repulsive van der Waals interaction. When you apply an electric field, you decouple them and you have 2 independent sets of charge fluctuations, and each one of them gives a repulsive van der Waals fluctuation. So you take 2 minus 1, it gives you 1. So this is the decoupling mechanism, okay? And actually, if you look at the, so this is the question, if you look at the large, if you look at the general behavior for a general system, actually, it's just beta E squared divided rho bar plus and rho bar minus, and the diffusion constants don't appear in the long-range interaction. But I've just told you why, because effectively you have a sort of a strange, it's not an equilibrium theory, but it's a pseudo-equilibrium theory where positive ions no longer interact with negative ions, right? So now what is the question?
How do you get the extra term than this previous one? No, the previous slides. Previous slides.
The previous slide, yeah?
No, yeah. The last one is.
This last one.
Yeah, it's not just yeah. So this is how do we get that other term? Yeah.
So this term this comes out of the theory as well.
Okay.
So when I write down this theory here, right? So I have 2 independent theories. This is for the n pluses, and this is the n minuses, right?
Yes.
So each of these theories gives me a long-range contribution, which gives me 2 times this, which cancels off with the attractive van der Waals, okay? And each of them gives me one of these terms. Okay. So this is where the factor of 2 comes from. If you just were, so this term here actually, so this is from the dynamical calculation. So you can see it's not just, the theory is not just working correct. This interpretation is correct for the screened part as well, right? So basically, so you have 2 long-range repulsions plus 2 attractive screened parts. And this is why you get rho m divided by square root of 2. There's a factor of rho. The density is it's changed by a factor of 2. Okay? Okay, so now, what happens if I put, so I always need to have at least 2, right? I can take, so I know I have a theory for, say, sodium chloride and calcium chloride, because this theory here would work for calcium chloride, just rho plus rho minus. But in principle, I could have calcium chloride and sodium chloride, right? So what would happen then? Now, if you assume that the Na plus will all move with the same velocity, right? Doesn't matter if it came from NaCl or CaCl2. Calcium will move in a different way to sodium chloride because it has twice the charge and it has a slow mobility. In principle, it could cancel, right? Very highly unlikely it would cancel, okay? And the chloride ions, they have their own velocities as well, okay? But it says that in that case, if I assume that the 3 species have different velocities, different bare velocities with respect to the electric field, they should decouple. Okay? So not only are the anions and the not only are the anions and the cations decoupled, the cations which have different mobilities will decouple as well. Yeah? And so that means that I should get an extra repulsion coming from a new charge density. And in fact, what happens is you can show analytically, you can't solve the equations in general, but you can solve them in the large E limit, assuming that they all have different bare velocities. Okay? You can show that the repulsive part of the Casimir interaction is n minus 1 zeta 3 over 8 pi beta h cubed. Okay? And actually, it's interesting, if you look at, there are experiments done by Carlos Drummond in Bordeaux, where you set a system out of equilibrium with an AC field, and you see very, very strange effects when you have large contrasts in mobilities in the ions. Okay? So this actually comes out. So this idea of decoupling seems to be robust. Okay? So the conclusions: driving can not only modify screening, but it can lead to long-range interactions. The model considers is rather simple, but the basic effects should be generic, actually just from the physical argument I'm giving you. And so the thing to bear in mind is that screening is a miracle. You should never think that screening, well, everything screens, right? It's accepted. You look at all the books, everybody says screening. But screening is a miracle, and it's a very delicate little miracle. It's destroyed by driving. So there are possible extensions. You can have systems with surface charges. So this is difficult because, I was assuming there were no surface charges in my system. When you talk to chemical physicists, they will tell you this is extremely difficult to do, to get neutral surfaces. Obviously, AC fields are interesting, much more interesting from an experimental point of view, because you start getting hydrolysis if you have electric fields which are too big, and also you could look at hydrodynamic effects. So I'll stop there and let you ask some more questions.
What if you had electric field in the perpendicular direction?
So it depends if your plates would be conducting or not. If you apply an electric field, a DC field in the perpendicular direction, it'll basically just generate surface charges, right? So basically, the electric field will generate effective surface charges. So you'll just be in a sort of situation where you will have, it'll be equilibrium because the currents will not flow. But obviously, if the plates were then conducting, then you would have a non-equilibrium situation. And obviously, if you have an AC field, so in the experiments of Carlos Drummond, he actually applies the field in this direction, but it's an AC field, and even if the electrodes are not conducting, the system is out of equilibrium. But if it's a DC field, then it will eventually just go to an equilibrium. It'd be like putting particles in a box with gravity, right? You would eventually have an equilibrium.
Just out of curiosity, this zeta 3, the 3 is due to the dipolar interaction, right?
Yeah, actually, so this zeta 3 actually, it's due to the dipolar interaction, but it's actually it's like a universal. If you look at any field theory, if you look at a field theory without mass in 3 dimensions, okay, and you just impose Dirichlet boundary conditions. So any fluctuating field which is massless, you impose fluctuating boundary conditions, you find this zeta of 3. So it happens for Neumann boundary conditions and for Dirichlet boundary conditions.
Nothing to do with the fact that the dipolar interaction in one of our cube. I mean,
I suppose it is somehow coming out of that as well, right? Because if you think about, if you write down it's obvious, yeah, it's coming out. It depends on the dimensionality.
So sorry, you meant scalar field theory with Dirichlet boundary conditions, is it?
Yeah, so if you just take a slab, right? If I just take where you get this zeta of 3. Here. So if I just take h equal to a half grad phi squared, right? Just take that massless theory and I just put it in a box, and I take this to be h, okay? And I just impose phi is equal to 0 here, phi is equal to 0 here. That's where you get the same, exactly the same interaction with zeta of 3.
Hello.
Hello.
Maxwell's waste energy answer. Huh? The slides on the Maxwell's takes energy answer. What are the different components of it?
This
What are the different components of it?
of the Maxwell stress tensor.
Yes, yes,
This is the dielectric constant.
yes.
This is grad, so this is EI, this would be EJ, and this would be E squared, right? Because E is grad phi.
Oh no, suppose sigma ijx, huh?
Yeah?
It is uniform at the point of x, or it has certain other components. Means the sigma subscript 1, 2, 3, or the xyz.
IJ is x, I is x, y, or z, right?
Oh, yes, yes, yes. I forget to as a height index. Yes, yes. Yes, yes. Thank you.
Okay, yeah, it's just, sorry, they're just the spatial indices, yeah? Yeah,
And the ij is
yeah.
I have just a question. Suppose I don't have salt ions,
Yeah.
and I have thermal Casimir pores, and if I apply a field like that, will this effect be there?
If you don't have salt, so you'd have no salt.
Yes.
So you just have this situation, and you apply an electric field across a dielectric.
Yeah, in the in the plane of the slab. I mean, what I am trying to say is the dipoles will be, the fluctuation will be along the direction. I mean, it will suppress the fluctuation of the dipoles.
Oh, you mean, yes, that's a good question, actually. So, yeah. So, actually, yeah. So, if you apply so I'm not looking at the effect. So that would be like a Chi3 effect, right? A modification of the dielectric constant by the electric field. That's an interesting point, yeah, because in principle, if I apply an electric field across a dipolar slab, basically you're polarizing the dipoles in the direction of the field, so they can no longer correlate with the field, but with the dipole. So, yeah, that's an interesting effect to look at, actually.
Okay.
And that would be something interesting to calculate, and actually even asked experimentalists, right? So the question is basically, if you apply an electric field in a slab, you polarize the dipoles, okay? So because the dipoles, okay, if it's a Gaussian model, it wouldn't work because it just shifts the average value and the fluctuations are the same. But if you took a Langevin model for dipoles, so dipoles which were, really saturated, so permanent dipoles. So yeah, so normally these dipoles do this, right? So they attract each other. And so if you apply an electric field, you polarize the dipoles like this and they can no longer correlate with each other. So you should kill off the van der Waals interaction.
Okay.
And you think you can sort of do some sort of calculations. And people do electrowetting and they apply the field this way.
Okay.
And I've spoken to experimentalists and I said, well, if you apply the field in the dielectric, you should be able to see a modification of the van der Waals interaction. And I think where it might be easiest to show up is if you do a droplet. If you put a droplet on a dielectric surface, and he experimented, right? And you apply an electric field in the dielectric surface, you should modify its dielectric constant. So you should change the wetting angle because you're going to change the the surface tension, which is dominated by the discontinuity in the van der Waals interactions. And I think Vincent Demery actually, they looked at the conductivity as well. You can look at the conductivity problem. You can actually take into account in the dipole, see the dipole model I wrote down was the easiest one, right? It was just, you know, p squared over 2 chi, but if you actually say p is fixed and it can only rotate, then you can get an effect of dielectric saturation. And I think it'd be, and I don't think anybody's tried to do that. And I've spoken to experimentalists before about this and said you should do the experiment on, try and look at how a droplet's contact angle changes when you do that. So if anybody here wants to do the experiment, I think that would be a good thing, because it's difficult to measure the forces, but the contact angle would be a good way of doing it.
So just to say that that you'll be here tomorrow as well, and I guess after that you'll be at ICTS. But
Yeah.
so David is around tomorrow for experimentalists to come and talk to him.
Yeah, I'm going to give a shortened version of this talk at the ICTS. So it'd be like the T20 version. We've got a test match today.
Yes, cricket. But he has one day more at RRI, so they're experimentalists you can talk to.
Okay.
Any more questions, students? I'm just going to go to this.
So I was just wondering, so in one of the slides you said that when you have the electric field and then the force on the ions is Q into E. So is it because you are in the Huckel limit, or will it be valid for every?
So it is just because it's because if you have an ion, right, in the electric field is E, the force due to the electric field is just Q times E. Now there are other forces due to the other ions. So E is the imposed electric field. So in principle, when you know, the exact thing to say is that if you work out the force acting on an ion, F is equal to Q times E, but this is the total electric field. So this is equal to Q times the external field, right? Okay. Plus minus Q times grad phi, where phi is the electrostatic field created by all the other ions. And actually, so this is when, so because of this effect, so normally you would argue that, you know, the conductivity of an electrolyte just be proportional, you know, the naive calculation of the conductivity of an electrolyte just uses this, but actually this is a back field, and it's sort of, it means that when the positive ions move forward, the negative ions try to drag them back. And so this is what, when you teach electrical conductivity, you just write that, you know, the force is Q times E, so the current is just equal to the velocity that you would get, which would just be the mobility times Q times E, yeah? So that's just the current, and you multiply that by Q in order to get the electric current. And so that calculation that's the naive calculation, but it's renormalized by the effect of all the other ions. So that's what I call the external force. So there are it's only electric, right? But the other part of the electric field is generated by the other ions.
Okay, thank you.
No, this setup you're mentioning, when you have this dielectric and you put this droplet and then you put this electric field. So typically how much electric field you have to put to see like a substantial variation of the this wetting angle? So that, I mean, is it measurable? Like
I'm worried now because you're asking me this question as an experimentalist. So I reckon if you use something which was ferroelectric or something like that, you would probably. So I mean, if you use glass, it would probably be really bad. But I guess there are presumably materials which, you know, have a strong dielectric response and perhaps show the saturation quicker.
Yeah.
I don't know. I mean, the electric fields might be really big. They might be. In fact, we looked at it for here. In order to see the effect we're seeing here, you can just about do it with a DC field, because you have to avoid, you know, you have to have very small separations, which gives you the possibility of having you can apply big electric fields. But obviously, you know, everybody knows that this would be much easier to do. The problem is the experiments are much easier to do in AC, and the theory is much easier to do in DC.
Okay. If there are no more questions, shall we thank David for a really interesting talk? and here from RRI.
Oh, thank you very much. Let's see. Wow. Thank you. Oh wow, it's got all the photos. Yeah, no, I bought a big suitcase, so it should be okay. Don't worry. Okay.
Yeah, we
Okay.
actually have